Hello and welcome to this section of the chemistry tutor where we're going to do our final titration problem. I hope up till this point you've gotten a lot of practice and a lot of experience with these titration problems. Never forget, the theme is really always the same. You have an acid, you have a base, they're reacting, and you're trying to find that equivalence point where all of the reaction is basically done and there's no more acid-base, it's all neutralized. You're trying to generally find that sweet spot where that actually happens. So in this problem, you read it, and again, much like the last problem we talked about, it looks like something a little different than what we've done before, but in fact, the core idea is the same. We have a 10 milliliter sample of battery acid. Battery acid, just in case you don't know, is sulfuric acid, which is H2SO4. Now we take this battery acid, this 10 milliliters that we started with, and it's diluted. In other words, we add water to it and bring it up to 100 milliliters with water. After we do that, we take 10 milliliters of this diluted sample, of this diluted acid, and we find out that little 10 milliliter sample requires 38.7 milliliters of potassium hydroxide, 0.238 molar potassium hydroxide solution in order to titrate it. The question is, what is the molarity of the original battery acid? So again, you've got a little detour here, and it's important to make sure you understand what the problem's actually describing before you try to set off and do anything, otherwise you're just going to get confused. You know, imagine you have a car battery. You open it up, which you should never do, by the way, because battery acid in a car is really caustic. It could really hurt you. But you rip off the top, and there's this really nasty sulfuric acid inside. So what do? You reach in and you grab 10 milliliters of this battery acid, this super concentrated battery acid, all right? You take that into the lab and you add water to it to bring it up to 100 milliliters. Now at this point, you have your battery acid and you add water to it. When you add water to it, you're not changing the amount of sulfuric acid there. All you're doing is watering it down. It's kind of like, we talked about salt. If you have a really salty, chicken soup or something, if you add water to it, you taste less salt, right? You haven't changed the amount of salt there, you just simply added water to dilute it. So we have the super strong acid, we add water to bring it up to the 100 milliliter mark. That's not going to change how much H2SO4 is in there, but it is going to bring up that volume and dilute it. Now once we have that diluted guy, that 100 milliliter, flask or something like that, containing this diluted sample, then we go in and dip out 10 milliliters of that dilution. And we take that 10 milliliters and we bring it into the lab, and then we start adding this base to it, this certain molarity basic solution, and we find out that it takes 38.7 milliliters of this base to titrate it, to fully react with the acid that's in there. All right, the question is, what is the molarity of the original battery acid, the original acid that we dipped out of the battery? So we're not interested in the molarity after we diluted all of it. We're interested in what is the molarity after we, if we actually rip that battery case open and look at what's inside of there. So you really need to backtrack in these problems. And I've kind of said that over and over again. When you do your calculation, you always start with what you know. What you know is that it takes a certain volume of a certain concentration base in order to titrate this guy. So we're going to end up starting in that direction, but even before we do that, we want to write down what this reaction is. So what we have is sulfuric acid, H2SO4, all right? And that's being added to potassium hydroxide. And let's just say, for the sake of argument now, it's in solution, and of course it is, because we know the molarity of the potassium hydroxide, we know we're adding a certain volume. So both of these guys are, solutions, aqueous solutions. And what do you think is going to happen? Well, the sulfuric acid is going to liberate some hydrogen. The base is going to liberate some hydroxide. So we know water is going to form. And so water is going to be formed. The only other thing that can happen is the potassium is going to come together with the sulfuric acid. So what you'll have, with the sulfate ion here. So what you'll have is KSO4. But before you move on, you need to make sure, are your subscripts correct here? You know the potassium is going to come out. You know the SO4 is going to come out. So a lot of students will leave it like this and say, okay, this is formed. But you can't forget what we learned in basic chemistry. How do these ionic compounds, what ratios do they come together? If you look at the periodic table, you'll see that the potassium always wants to have a +1, and the sulfate ion always wants to have a -2. So if this wants to have a -2 and this wants to have a +1, if you do the crisscross, this 2 from the sulfate needs to come down. The 1 from up here comes here so you don't see it. So really it forms K2SO4. This is really important because if you don't do that right, then you're not going to balance the reaction correctly. And if you don't balance the reaction correctly, then your stoichiometry is wrong and you're going to get the wrong answer. So when you're looking at what's going to form, yeah, you know sulfate's going to come down, you know potassium's going to come down, but what ratios, you know, what this is telling you is that for every sulfate ion, 2 of these potassium ions are going to be, you know, in that ratio. So 2 to 1 as far as these go. So that's why you have the 2 down here. And you get all of it from the charges on the ions and the elements there from the periodic table. So we're going to get this. We're going to say it's an aqueous solution. And then, of course, we're going to have our nice, let me go ahead and give me a little more space here. And, of course, that's liquid. So once we have it all written down, then we need to try to make sure and balance it because everything needs to be balanced. So we look at this and we say, well, I have K2 here and I have K here, so I know I'm going to need a 2. And then I start trying to balance. I have 2 hydrogens here and 2 hydrogens over here. The only hydrogen I have over here is 2 of them, so to balance that, I'm going to attempt to put a 2 in front of the H2O. So let's start over. 2 hydrogens, 2 hydrogens. That gives you 4 on the left. Here's 4 hydrogens on the right, okay? Then you have SO4. You can think of that as just one grouping of a sulfate ion. You have SO4 here. That's one grouping of a sulfate ion, so that's balanced. 2 potassiums, 2 potassiums. And then you have 2 oxygens here and 2 oxygens over here with the water. So that's balanced. And I've already counted this hydrogen, so I don't need to do that again. So this reaction is balanced. Notice what this says. It says that for every 1 mole of sulfuric acid, I'm going to require 2 moles of potassium hydroxide, right? So it's a 2 to 1 relationship between, you know, acid and base like this. Notice that this 2 basically directly comes about because of the K2SO4 there. It all started whenever I noticed that I had 1 potassium here and 2 potassiums here, so I started the balancing process. If you had not constructed this guy correctly with the correct subscript there, then the balancing of the reaction would have been wrong, and that's going to end up affecting everything later. So you always have to take things one step at a time. Make sure you're using the rules appropriately. It's all building upon what we've learned before. This is nothing new. And if it seems foreign to you, go back and watch those sections before on forming compounds because we talked about all that before. So now we've got the reaction, we know what's going to happen, and I've given you the advice over and over again that we should start with what we know. So what do we know? Yeah, we have an acid here and all that, but what we really know is that it requires this much volume of a certain concentration of potassium hydroxide. That's how much base is actually required. So we're going to start there. So we know we need 38.70 milliliters of what? Of KOH solution. That's how I write it down, KOH solution. That's what I'm starting with. All right. And let's go ahead and use the molarity to convert to moles. So what this is telling me, 0.238 molar means 0.238 moles per liter. All right, but before I can really use it, I know I've got milliliters here, and this is going to be moles per liter. So before I can really use it, I need to go from milliliters to liters. So what you do is you just say 1,000 milliliters of KOH solution is 1 liter KOH solution. You know? And we cancel milliliters with milliliters. So now if we stop the calculation, we really have how many liters of potassium hydroxide solution? Now let's use the molarity, 0.238 moles per liter. 238 moles of potassium hydroxide for every 1 liter of potassium hydroxide solution. Okay, so I have liters of potassium hydroxide canceling with liters of potassium hydroxide. So if I stop the calculation now, I've started with how much KOH solution is required, and I've calculated how many moles of potassium hydroxide are actually needed. So that's how many moles of KOH are actually in that volume of solution that we said it required. All right? So now we're at the level where I know how many moles of base I actually need. So now I can jump up to my reaction, and I know now that for every 2 moles of KOH, I require 1 mole of sulfuric acid. So I continue my calculation down here. right? Just kind of pretend this is stuck on the end. So I've got moles of KOH on the top. Now for my reaction, I know that it takes 2 moles of KOH for every 1 mole of H2SO4. So it's basically a 2-to-1 arrangement. So the moles of KOH cancel with the moles of KOH up here. So if I stop the calculation now, I reach a very important result. What I figured out now is that, yes, this titration required so much base, okay? What I've calculated, if I stop here, is how many moles of acid is basically reacting with that base that I'm given in the problem. How many moles of sulfuric acid is required? It has nothing to do with the volume, it has nothing to do with the molarity. It's how many moles of H2SO4 is actually needed. So I can actually erase this because I'm going to stop my calculation here, because that's important. You know, ultimately, I mean, take a step back. What am I trying to find? I'm trying to find the molarity of the battery acid. Molarity of anything is moles of substance divided by volume. Moles per liter, right? I have calculated the moles of H2SO4. That's an important result that's going to feed into my final calculation. So let me stop there. If you take 38.7 times 1 divided by 1,000 times 0.238 divided by 1 times 1 divided by 2, then what you're going to get is 0.0046 moles of H2SO4 needed. And what I mean by needed is I'm just saying that's how much is required to fully react and titrate with this much base. That's how much of that acid is needed. Okay, so this is an important result. I already told you why, because molarity is moles per liter, and I've calculated something that resembles moles of H2SO4. But the rest of the problem, it really is an exercise in logic. The rest of this problem is an exercise in you understanding what it's telling you. All right, so if you have this much base, and I've calculated how many moles of H2SO4 are needed to react with that much base, I need to work backwards through the problem to figure out what the molarity of the original solution is, right? So what I know, let me write down something to kind of lay this out for you. And I admit, you know, you need to think about this for a few minutes. You know, if your first temptation, because you're not really sure what to do at first. You're not sure if you should use this 10 milliliters or if you should use this 100 milliliters or if you should add them or subtract them, or what volume do you need to use to calculate along with this guy in order to find the molarity of that battery acid. But you need to think logically through it. So what I've written down here is a couple of little statements, and hopefully I can lead you to the solution. What we've calculated here is that 0.0046 moles of H2SO4, okay, this is how many moles of H2SO4 is in the final 10 milliliter diluted sample. All right, don't forget what happened here. We took some battery acid, we ripped open a battery case, we dipped out 10 milliliters. Then we added water to it to bring it up to 100 milliliters, so we diluted that guy. After we diluted it, we took 10 milliliters of that, and that is what we actually titrated with. So when we calculated how many moles of H2SO4 were needed, that's how many moles of H2SO4 were in this final diluted sample after we dipped out the 10 milliliters, right? Because that's how many moles were in there. The reason we know that is because it took this much base to react with it. So that tells you, since everything's locked in terms of the reaction, if it took this much base, then this is how much H2SO4 must have been in this final 10 milliliter sample after we diluted everything and got the final thing that we're actually trying to react with. Okay? So what this tells you next is that, all right, so let's backtrack a little bit further in the history of what we did here. If that was how many moles were in the diluted guy, then prior to us dipping out our 10 milliliters, when we had our larger vat of 100 milliliters, then since this is 10 times the volume here, then in the larger bucket, then I should have had also 10 times the moles of H2SO4 in this 100 milliliter sample before I dipped out some more. So what I'm going to do is illustrate that with multiplying by 10. That's what times 10 means. So what I also know from this is that when I take this guy 0.0046 and multiply by 10, I get 0.0461 moles of H2SO4 in the 100 milliliter diluted sample. Make sure you understand that. What we're saying is, look, this is how much 0.0046 moles of this H2SO4 was in the final 10 milliliter diluted guy that we actually reacted. So if that's true, then before we actually dipped out 10 milliliters, if you look at the larger volume that we actually dipped out of, then we must have had 10 times the amount of acid there. Because when you have a certain concentration of acid, you know, it's all mixed in the bucket, right? So I had 100 milliliters, I dipped out 10, that's what I reacted. I know how many moles of H2SO4 were in the final 10 milliliter sample. So if that's true, if I multiply by 10, I'm going to find out how many moles of H2SO4 were in the larger bucket, right? Because it's 10 to 100. That's 10 times larger. That bucket's 10 times larger. So I found out that 0.0461 moles of H2SO4 was in this bucket. So now when I read my problem again, it says I have a 10 milliliter sample of battery acid, right? 10 milliliter sample. And then I dilute it and bring up that volume to 100 milliliters. So if you think about it, if you have a battery here and I dip out pretend this is 10 milliliters, 10 milliliter sample. This 10 milliliter sample is going to contain so many moles of H2SO4, all right? And then I bring it over there and I add water to it, bring it up to 100 milliliters. When I add water to it, I don't change how much H2SO4 is in the 100 milliliter bucket compared to what was in the original 10 milliliter sample of battery acid. I don't change how many moles of H2SO4, I just change its volume. So because of that, if I know that 0.0461 moles of H2SO4 were in here, then I also know that I had 0.0461 moles of H2SO4 in the original 10 milliliter sample. Because adding water to it doesn't change how many moles, of H2SO4 you have. So what I really know, kind of a conclusion, what I figured out here is 0.0461 moles of H2SO4 in 10 milliliter battery acid sample. Now this is not this guy. This 10 milliliter sample, that was done later. I'm talking about the original 10 milliliter guy that we dipped out of the battery. So molarity, big M, is moles over liter. I know how many moles of battery acid, 0.0461, that's moles. Let me do moles. Okay, what is the sample? Well, when I look back up here, it was a 10 milliliter sample. You can't put 10 down here because that's in milliliters. You need to put it in terms of liters. When you convert 10 milliliters to liters, you get 0.01. Because basically you take 10, you divide by 1,000, so you're going to get 0.01. This is liters. So when you take 0.0461 and you divide by 0.01, then what you're going to get is 4.61 molar H2SO4 battery acid. So pretty high molarity, pretty high concentration. And that is the molarity of the original battery acid. So again, you need to notice the actual math here, like most of the chemistry part of it is pretty short, and the rest of it was kind of a logical string of thinking. And I'll admit, even for me, I had to think about it for a few minutes. I had to think backwards from the final state and kind of work backwards to the beginning to see what made sense. And ultimately what we did is we opened up a battery, we took 10 milliliter, tiny little bit of 10 milliliter sample out of it. Then we added water to 100 milliliters. Once we added that water to it, we didn't change how much H2SO4 was in there. That was locked in from the beginning, right? Once we get this guy, this larger thing, then we take 10 milliliters out of that, and that's what we react. So really what you're doing here is you're changing the concentration of the acid by adding all this water and then dipping out a new sample. The reason the problem's confusing is because you have 10 milliliters of the original battery acid and then you dip out 10 milliliters after you've diluted it. That makes it convoluted to think about. But once we do that and we react it, we find out it takes this much of a base to titrate it. So I start out with this many milliliters of the base, convert to liters, and then I use the molarity to find out how many moles of KOH were required to titrate, and then I used the reaction to find out how many moles of H2SO4 actually reacted with it. So what you find out is that forevermore, for the actual reaction, and after we dipped out this tiny little sample and reacted it, it actually took this many moles of H2SO4. So then it becomes a logical thinking game. If 0.0046, if I know how many moles of H2SO4 were in this little sample after I dipped it out, then I immediately know how many moles of H2SO4 was in the larger sample, because I had a big bucket and then I dipped out a smaller sample. And so I know that the big bucket's 10 times the small little thing I dipped out. So if I know how many moles are in here, then I just multiply times 10. I know how many moles of H2SO4 are in here. And when you multiply by 10, you get this number. And then you go back and you look at your problem and you realize is that, hey, whenever I started with my original concentrated acid and I added water to get to here, I didn't change the amount of H2SO4 in there. I just added water. I know what this number is now, 0.0461 moles. So I just take 0.0461 moles and I divide by the original volume that I had, 10 milliliters, and that's going to be the concentration of the original battery acid. Basically, I started out with a high concentration, and then once I added all that 100 milliliters of water to it, I diluted and lowered the concentration, and then I took that final concentration, dipped out a certain sample, and then I did the reaction. So I hope that's clear to you. Sometimes in chemistry, once you get past the sort of like the initial cookie cutter problems, you really need to do a little bit of independent thinking, and this is a good example of that. You can do it, but then in order to do something with the answer and kind of work your way back up to what they're asking, you have to kind of think about things a little bit. So they're not always these problems are not always going to be in these little kind of these buckets like, oh, this one's done this way, this one's done this way, this is very unique. You know, you may not ever see this problem again, but the thinking process behind understanding concentration, understanding what a mole is, understanding what molarity is, all that stuff is very important. Once you understand those concepts, you can solve all these problems. So that's going to do it for the acid-base titration problems. The next few sections, we're going to switch gears a little bit and talk about a different kind of reaction that's also very, very important that you'll definitely study in your class, and that is called precipitation reaction. So follow me on to the next section where we'll start to build that groundwork so you can understand those types of reactions in chemistry.